Hello. Numbers are the most fundamental notion in mathematics, but you probably guess that not all numbers can be represented in computer's memory, simply because we have infinity of numbers and computers have no infinite memory. In this presentation, we will look into mathematical sets of numbers such as natural, integer, real, and even complex numbers. And then we'll move on to computer representation of various types of numbers. So we will first of all look into signed and unsigned numbers and fixed and floating point numbers. At the end of this session, I will also introduce representation of characters or texts in computer's memory. So, what are the most important sets of numbers in mathematics? And yes, one of those sets are imaginary numbers, but these are not of great importance for computer science. The first set is of natural numbers, which are symbolized in mathematics with a big N symbol. But they are actually less important in computing because these are numbers that you could count on your fingers if you had infinite number of fingers. So these are numbers starting from 1, 2, 3, 4, and so on up to infinity. For programmers and for computing, it is much more important to look into non-negative integers, symbolized in maths as n0, and known in computer science as unsigned numbers, 0, 1, 2, 3, 4. So it's much more natural for us to count from 0 to infinity as well. So that's one important set of numbers, and another are integers, big Z, also known as signed numbers. So these are both positive numbers and negative numbers. All these sets shown here have one thing in common. There is no representation of fractional parts in it. So it's 0, 1, 2, but not half, not 1/3. Mathematics provides another fundamental set of numbers called real numbers. And real numbers are further broken down into rational numbers and non-rational numbers. Rational numbers are all fractions. So rational numbers are created by dividing two integers by themselves. So it's like 1/2, 1/3, 1/4, but also 2/2, 2/3, 2/4. Generally, rational numbers are all numbers that can be represented as a fraction. And we also have non-rational numbers, symbolized by R not Q, which cannot be represented as a fraction in terms of two integers divided by themselves. Non-rational numbers are numbers like square root of 2, square root of 3, the number pi, the number e. For example, the number pi, 3.14159265, and so on, it has infinite number of digits after the decimal point. This is just a small portion of this number pi. Okay, you can see more numbers in this website. Right here, there is a longer extension of the number pi. Let's have a look how long it is. Oh, it's too long to just scroll down. I will take this and go down, 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 down. You know what? It's the number pi with precision to the 1 million decimal digits. It's 1 million decimal digits displayed here. 1 million decimal digits is still something that a computer can represent in its memory, and it would be about a megabyte of memory, so not so much. But of course, this is just a very small portion of the real complexity of the pi number. We've just seen 1 million digits, but 1 million digits, it's still just a small, infinitely small fraction. Million digits, it's still just a beginning of the real pi number. It's infinitely long. We also have numbers beyond the real number, and this is something we mentioned in the initial session on maths this year. It's the result of square root operation performed on the negative number 1. So square root of negative 1 is a special imaginary unit called I like imagination. The characteristic of I is that I squared is equal to negative 1. This is, of course, an abstract creation of mathematicians, very useful in some aspects, in some applications, but these numbers, first of all, have no usual representation in typical programming languages, and more importantly, these numbers have no particular application in game development. So we will not look into complex numbers anymore, and let's go quickly to number representation in computers. So first of all, computers are binary because binary operations are easy to implement, because binary states 0 or 1 are easy to represent. For example, 0 can be represented by no voltage or 0 volts. 1 can be represented by some positive or negative voltage like 5 volts. Length of binary representation, which is actually a problem with binary numbers if we would think about using them in everyday life, is not a problem for computer machinery because all binary digits are processed simultaneously. So the length of a binary representation does not affect efficiency. Some basic terms. Bit. What is a bit? Bit is the smallest unit of information, either 0 or 1, or bit also a counterpart of a single digit in binary notation. Octet. Octet is 8 bits. An octet can hold numbers from 00 to FF hexadecimally. So FF stands for 8 bits of 1. So it's decimal numbers from 0 to 255. What is a byte then? Byte is the smallest unit of memory that can be addressed by a computer. This is the official definition of the byte, but also you can notice that it is nearly always 8 bits. So in practice, byte may be used instead of octet. And this is how we will be using it, because I think all modern computers use 8-bit octets as the smallest units of addressable memory. There were computers in the past in which such a smallest unit of memory had a length of 7 bits, and this was we could say this was a computer with a 7-bit byte. But now byte and octet is practically the same thing. Then we have another convention, a kilobyte. A kilobyte quite often will not be exactly 1000 bytes. And in old good times, when I was taught computer science at a university, it was pretty much clear that 1 kilobyte is exactly 1024 bytes. Why such a strange number? Because 1024, this is 2 to the power 10. And of course, it makes a lot of sense to calculate, for example, the size of memory in powers of number 2, because this is how memory is usually organized. So there was a nice agreement that the word kilo in computer science, instead of 1000 like in SI system in physics, in computer science it used to mean 1024. So megabyte, 1 million byte was in fact 1,048,576 bytes, or 2 to the power 20. Gigabyte was 2 to the power 30, and terabyte was 2 to the power 40. Unfortunately, technically, this is not anymore true. The standardization organizations reconsidered this system, and the judgment was that kilo, mega, giga, tera have to mean exactly the same thing as in kilogram, kilometer. So kilo is 1000, mega is 1 million, and so on, so on. So according to the latest standards, new standards, kilobyte is exactly 1000 bytes, megabyte is 1000 kilobytes, gigabyte is 1000 megabytes, and terabyte is 1000 gigabytes. And we have new units with old style 1024 multiplicity, so 2 to the power 10, but the name has been changed from kilobyte to kibibyte. So 1 kibibyte is 1024 bytes, 1 mebibyte is 1024 kibibytes, and so on, so on. This name kibi is an acronym from kilobyte binary, mega or kilo binary byte, mega binary byte, giga binary byte, and so on. The problem is that very few people use this new standard. I hardly ever heard anyone talking about kibibytes, mebibytes, and so on, so on. So this decision by the standardization committees only created quite a lot of chaos, because now when someone mentioned a kilobyte, you will never know if it is the old meaning, and kilobyte is 1024 bytes, or a new meaning, a kilobyte is 1000 bytes. One thing that is absolutely sure, that producers of hard drives will use the new standard, because if they produce a hard drive and this hard drive is, let's say, 1 terabyte, in tebibytes the number of tebibytes is slightly smaller. So actually you can just fit more new standard terabytes or gigabytes into the same amount of memory. So because of marketing reasons, they definitely would prefer a new standard of gigabyte, terabyte, and so on. But basically you have to be careful, because now it's not entirely clear what a megabyte or gigabyte means anymore. All right. Joke for programmers. And some more terms. A word. What is a word? Word is a set of bits of some fixed length. So I know that it's a very vague definition, and but this is how it is defined. Basically, a word is typically the typical size of numbers, or accuracy of numbers used in the given architecture of computers. So early computers, which were in use when your lecturer was very young, were called 8-bit computers. What does it mean, an 8-bit computer? It wasn't a computer which had only 8 bits of memory. It was a computer that used internally, most often, data were organized in 8-bit long words. So, for example, transfer of data between the processor and memory was based on sending 8-bit words. Okay, of course, sending 8-bit words was not very efficient, so these computers were quite a long time ago replaced by 16-bit computers, 16-bit architecture, so architecture with a 16-bit long word. Then we had 32-bit computers. Some computers still use this architecture, and most modern computers and mobile phones and tablets are based on 64-bit architecture. Register is an electronic circuit capable to store and read words. So we now have a clear situation. A 64-bit computer means that this computer works or is equipped with 64-bit registers that can store 60-bit long words. And there is also one more important term here, bus. Bus is a vehicle that you can use to ride home. Not, of course, no. In computer science, bus is an electronic circuit used to transmit words between components of a computer. So bus basically is a transmission medium between two different registers or between a register and memory. And so we now have a clear situation. Architecture, 32-bit architecture, 64-bit architecture means that internal registers and internal buses will be of that width, of that number of bits. And one more term, memory. Memory is where all data are stored. Practically, memory is just a huge container of multiple registers. And this is an anatomy of a word. This word is, as you can count, it's 32 bits long. So it's still, even in 64-bit architecture, still most often software will be using 32-bit long words. So this is a word of the length 32 bits. Now, some very important things. First of all, bits are always counted from the right to the left. Okay, so bit 0 is exactly here at the right end of this word, and bit number 31 is here. The second important thing is, if the word is 32-bit, this means that the bits hold names or indices from 0 to 31. From 0 to 31, we have exactly 32 bits. 0, 1, 2, 3, 4. If you count up to 31, you will count 32 times. This word can be decomposed into 4 bytes, 4 8-bit long bytes, and these bytes will again be numbered from the right side to the left side, and because we have 4 bytes, they will be numbered byte 0, byte 1, byte 2, byte 3. There's no space for byte 4. Okay, so from 0 to 3, these are 4 bytes. We also have 2 words, and in this case, the word 0 and word 1 are 16-bit long words. And this is a kind of chaotic terms now, because I've just told you that a word can be 32-bit long, 64-bit long. Okay, there's one tradition connected with a company that you perhaps heard about. This company is called Microsoft. And in that tradition, word is a 16-bit long word. And if something is 32-bit long, it's called D word or double word. So this terminology can be a little bit confusing. Sometimes there is one word used to describe two different things. You have to get used to this. Okay, this is the professional world of computing. But basically, the take-home message from this slide is you always number bits and any other units from the right to the left, and you always count them from 0 to n minus 1, where n is usually a power of 2. For example, 32, for example, 4, and so on, so on. 32 or 64 bits. What decides is the size of internal registers, but some registers will be up to even 256 bits and more. So it's a rather typical size of internal registers. But it's also size of data bus. Data bus is used to transmit data across computer components. And we have also size of address bus used to address internal memory. And quite interestingly, the size of different different buses can differ. So we can have a computer with 32 bits data bus and internal registers, but 64-bit address bus. Most software still operates on 32-bit words, even if it works on a 64-bit architecture, because this can represent integers up to 4 billion, so quite a big number. 64-bit bus and registers may speed up data transmission, storage and reading, but not as significantly as we might think, particularly if software still operates on 32-bit words. But 32-bit address bus, so the bus used to address internal memory, can limit the size of internal memory to 4 gigabytes per process. There are techniques to provide more memory with the size of address, but for a single process, so for a single program, this memory will be limited to 4 gigabytes. If you think, for example, about mobile apps, would they often really exceed 4 gigabytes memory on a mobile phone? But on a PC, 32-bit address bus can be narrow actually. So 64-bit buses are more and more popular, but it is not so much because of making computer faster, but rather more flexible, more functional. The most important term I would like to discuss today is the data type. This is this descriptor added in front of your variable name in your typical C++ or Java program. The data type is defined by a set of values that you can assign to the variable and a set of operations that you can perform on these values. We will be looking into the internal representation of data types. In regard to the mathematical sets of numbers that we discussed earlier in this lecture, the integer numbers are represented in computers by so-called fixed point or integer data types. The real numbers are represented by floating point types. This distinction is important because in computer we have no representation for, first of all, some very large integer numbers. So our fixed point data type is different from the mathematical idea of integer numbers. But in case of real numbers, first of all, we have no representation, no precise representation for all non-rational numbers. So such numbers like pi, square root of 2. And we also have no representation for nearly all rational numbers, so typical fractions. I think you may need some explanation why I thought nearly all rational numbers, if in fact we have plenty of rational numbers that can be represented in computer's memory. But ultimately we have infinity of rational numbers. And mathematicians say nearly all every time they mean infinity except a countable number of cases. So even if the number of cases, the number of numbers, real numbers that we can represent in a computer memory is huge, really huge, but it is something that you can count. So compared to infinity is nearly nothing. And this is why we say nearly all rational numbers cannot be represented in computers' memory. We can even say more. Nearly all numbers between 0 and 1, or nearly all numbers between 1 and 2 cannot be represented in a computer. So what can be? First of all, fixed point or integer values. This is a subset of integer numbers limited by the size of the computer word. The table in front of you shows a grid of fixed point or integer data types commonly used in C++ and other similar languages such as C, C# and Java. They are categorized into, first of all, 4 size categories, so from 8 bits to 64 bits, and also divided into signed types and unsigned types. Just as a reminder, signed type is a type that includes both negative and positive numbers, and an unsigned type is a data type that contains only positive values and 0. So in other words, non-negative numbers. It's easy to notice that the bigger size, the wider range. So for example, 8-bit signed range is only from negative 128 to positive 127. But also, a corresponding unsigned type will have a range which is shifted towards the positive side of the number line. What I mean, the difference between the minimal and maximal value in signed and unsigned type of the same size is identical. But because the signed range has to share all the values between negative side and the positive side, then there is a range of numbers, bigger positive numbers that can be represented in the unsigned type, but are beyond the range of the signed type. Of course, the decision which of the two types, signed or unsigned, which one to use, will depend on many aspects, but basically if you need negative and positive numbers, you definitely should choose signed range, signed type, and sometimes when you need a little bit longer range of positive numbers, this may be the reason to choose the unsigned type. There is a big difference in the range of available numbers depending on the size of the data type. So 8-bit, from the name of this data type, which doesn't even include the word int, it's char. Char is an abbreviation, a shortcut from character, okay? Short for character. This is a very small range because this data type is primarily used to represent characters like letters, interpunction, spaces, and also digits. Okay, but still it is considered a fixed point integer data type, so you can add char values, subtract, multiply. All the arithmetic is exactly the same as in regular integers. 16-bit short int covers a very useful range of numbers, and in the era of 16-bit architecture, it was the most popular integer data type. But anyway, it is easy to exceed this range, and the current history of NHS failure to store test and tracing data because the size of the file was limited to slightly more than 16,000 shows that these numbers like 16,000, even 60,000, this is not a really big number. So in many different situations, you would rather prefer the long int data type, which provides in the signed range, it's about negative 2 billion to positive 2 billion, and in unsigned range, it's over 4 billion. Okay, so quite a good range of numbers. And indeed, the long integer is currently the most often used, the default integer data type used in modern computers. There is also 64-bit long data type, rarely used because this type of precision, this type of really big numbers is very rarely required. Integer data types are so important that the names can often be shortened. So instead of short int, it's enough just to have short. Short and short int means the same thing. Long int, it's just long. Long int, it's just long. And similar situation with unsigned. Our most important, most popular data type, long int or simply long, can also be called simply int without long. And this is exactly the same thing, int or unsigned int. And in case of unsigned data type in C++ and C and similar languages, if you name a data type unsigned, this will mean the same thing as unsigned long int. So in many cases, you don't have to use a long series of words, and some shortening is absolutely acceptable. It is very important to notice here that signed types, so integer data types that can represent negative numbers, use 2's complement code, the special way of representing negative numbers in binary representation that we discussed in one of the previous lectures. What about real numbers? In case of integer data types, they could represent every integer number within a given range. But talking about real numbers, precise representation of non-rational numbers, such as pi, is impossible. And pi is not a big number, so it's not a problem with representing very huge numbers, but small numbers, which are simply difficult or impossible to represent. Please note that there is infinity of rational, not even non-rational, rational numbers between 0 and 1. There is infinity of them. So computers can represent only a relatively very small, infinitely small percentage of all possible numbers. And this is why we say that the real numbers representation in computers is sparse and limited. Moreover, we have to use a special representation that is sometimes called scientific representation. So, for example, the first number here is a huge number. It's a so-called Avogadro number. It's a number of particles in a mole of substance. It's 6.023 times 10 to the power 23. So it's 6 and 23 other digits with 0, 2, 3 in the beginning, then 20 zeros. Okay, so it's a huge number. But thanks to using this kind of notation, times 10 to big power, we can represent big numbers in a concise form. So here you have 3 examples: 4.2 times 10 to the power 1. Okay, 10 to the power 1 is 10. So 4.2 times 10, it's 42. Okay, so in this case, this notation is not very effective because 42 takes a smaller place, but Basically, it's just showing that it is possible to represent 42 in the scientific representation. And the third example shows a very low number, very small number, 0.000234. What's important is that in this notation with 10 to the power and in computing times 10 to the power of is replaced by this letter E. So 6.023 E23 means the same as 6.023 times 10 to the power 23. The important thing is that we get rid of all the zeros. Whether the zeros are on the right hand side of a number, and in case of a big number like Avogadro number, or if a very small fraction starts with a lot of zeros, we always can concentrate on the most significant digits, and then we just add the information plus 23 zeros at the end of the number, or maybe 3 zeros in the front of these numbers because it's a very small fraction. This scientific representation is used to internally represent floating point. So the general representation looks like this: S times b to the power e. Now, what is S? S is so-called mantissa, also known as significant, coefficient, or fraction, and this is what provides digits to a number. It affects the precision or density of the number representation in the real domain. Then we have exponent. Exponent, it's the power of the number 10, and it affects the range of numbers. So a big, high exponent means that we are talking about a very huge number. Negative exponent means that we are talking about a fraction, right? And b is the base, most often 2, sometimes 10. Okay, so 2 and 10 are commonly used to represent floating points. And here is an internal structure of a so-called single precision number. According to international standard IEEE 754, the base in this scientific notation is 2. 1 bit is reserved to represent sign, negative or positive. Exponent is 8 bits, so we have values between negative 127 to positive 128. Of course, in this case, we are talking exponent will provide the power of number 2, so it's times 2 to the power 128. Mantissa, so the digits, the content of the number, is 24 bits. Okay, it is an equivalent of between 6 to 7 decimal digits. Total length of this single precision number is 32 bits, or 4 bytes. So 4 bytes you have to provide to store a low precision or single precision number. The range of values is not so easy to specify as in case of integer numbers. So first of all, in case of floating point, it's important to know what is the minimum positive value. So this is the minimum value which differs from 0. And this is around 1 times 10 to the power negative 38. So it's 0.37 zeros and 175 and so on. So it's a very small number, so we can say that it's a reasonably precise representation. The maximum value, so the largest number that you can store as a single precision number, is 3.4 times 10 to the power 38. Another representation called double precision number, according to the same international standard, it's similar. The base is still 2, 1 bit for the sign, but the exponent now is 11 bits. Mantissa is 53 bits, and it stands for about 15 to 16 decimal digits. Total length is 64 bits, or 8 bytes. and look at the minimum value and maximum value. It's the minimum value is like 0 point more than 300 zeros and 222507. So it's incredibly small number. Maximum value is 1797, again more than over 300 zeros. Okay, so it's a huge number. So this representation can provide huge numbers with a very good precision. Please note that this precision here, the minimum value, this doesn't say that we will have this kind of density of representation throughout the whole range, because we always have only 15 to 16 decimal digits. So if we are talking about really huge numbers, okay, like this number here, all right, this is a number that requires more than 300 digits to represent. And all these digits, apart from 15 or 16 initial digits, will be 0, okay? So the representation of the realm of real numbers as a computer-based floating point has this feature that small numbers will be represented incredibly densely, like this, okay? And the bigger number it is, the bigger range we are looking at, this density will be lower and lower. So it is, as I called it, limited, scarce, and not uniform, okay? Small numbers are represented very densely, big numbers not so much. In C++, or languages similar to C++, we can choose between 2 or 3 data types. 2 or 3 because float and double data type are the representations that I've just showed, and they are quite popular. So float is quite fast, quite reasonable in terms of the range of numbers, but sometimes the accuracy offered by float numbers is not enough. And then you can jump to representing floating point numbers on 8 bytes as a double value. Double value has incredibly large range, incredibly high precision, and it's a very good data type. But in a rather unlikely case, it would be not sufficient. You have another data type, which I didn't even show you internal structure of this. It's called a long double, and it takes 12 bytes. But as I thought, for most practical reasons in gaming, you will be using either float or double. The next topic is not about numbers, it's about characters, and it's about texts. Okay, so characters, letters, digits, punctuation are represented by integer values, and you saw them because in the table with integer data types, the first data type with the size of 8 bits was called char for character. Of course, we don't have any naturally occurring way of attaching numbers to characters, so we need some kind of coding. And the standard code used in computing globally is called ASCII. ASCII stands for American Standard Code for Information Interchange, and it's important that this code is American. I will get back to this topic in a moment. Other surprising feature of ASCII code is that it only represents characters with codes from 0 through to 127. So it's not filling entire bytes or 8 bits of information. ASCII representation, typical ASCII representation is 7-bit only. And you may remember from one of the previous lectures that, no, actually it's earlier in this lecture, that in old times, byte and octet were two different things because byte was 7-bit long. And the reason for that was that we only needed 7 bits to represent ASCII code. And indeed, if you think about all the letters of the English alphabet, there are 26 uppercase letters, 26 lowercase letters, plus 10 digits, plus about 20 interpunction. It's 128 characters is more than we really need in the English language, of course. So this is ASCII. And now the problem with ASCII is that as the American coding standard, it does not include international letters, letters coming from a different language. So the problem basically is, if you look at this sentence, pchnąć w tę łódź jeża lub 8 skrzyń fig. It was a Polish sentence. Polish is my original language. And this sentence is special because it includes all special, so untypical letters of the Polish language. We have several other languages here, like German, which I don't dare to read, Turkish, and Greek. Greek language is particularly interesting because it's using a totally different alphabet. And we don't even touch here a real challenge like Japanese or Chinese languages, which not only use a different character set, but this character set is incredibly large if compared with our Latin or English alphabet. So, international letter codes were not included in the original ASCII code. So the solution was quite easy because original ASCII, 7-bit ASCII, there were characters coded from 32 to 127. Codes from 0 to 31 were reserved for special purposes, but there were some unused coding positions from 128, no. In the range from 128 to 255. There is some space there, but obviously it is not sufficient for all possible languages. Therefore, there were many different types of codings proposed for various languages. The problem was like this. If we are using different standards, and we code a text in one standard, and this is the correct Polish sentence, and then it is decoded using the wrong standard, what we get is something like that. And I can tell you, it's very hard to read for a Polish person. So the first problem is with a variety of different standards. Some of them you can see here, so-called ANSI code page 850 was for Western European languages. Please note that Western Europe is not just English, it's French, it's German, it's Spanish, it's Italian. All these languages, now all the whole family of Nordic languages, these languages provide a range of funny characters, different than English characters. Then there is a 852 code page specific for Slavic languages, and a competition to this page, 1250, which was specifically Polish, 737 with Greek alphabet, and so on. So as you can see, many different code pages. Code page stands here for coding standards. And a lot of opportunities to confuse things and decode them not in a proper way. Solution is called Unicode. Every reasonable writing system, including Klingon, is represented in Unicode. Unicode is a 16-bit representation, so we have 65,536 combinations. Stop. This is a little bit a myth about Unicode. It's not so simple, and actually Unicode has far exceeded this limitation of 65,000 characters. But let's start with some basic stuff. Each character is coded as a so-called code point. So, for example, U plus, this is how they are described, and please note that these numbers here are hexadecimal. So U plus 0639, it's a Arabic letter Ain, I hope I'm pronouncing this letter properly, and U plus 0041 is the English letter A. So here you have a representation of the hello. 5 letters, it will be 10 bytes because each letter is coded on 2 bytes. Additionally, there is a small problem with this because, for example, the number 0048, which is the uppercase H, can be either represented as 0048 or 4800. These 2 bytes can be swapped. And actually one of those representations is quite natural in Windows system. The other is quite natural for example, MacOS. So finally, there is a agreement that each file coded in Unicode will always start with either FEFF sequence or FFFE sequence. If it starts with FEFF, this means that the sequence of the bytes within the 2-byte word will be like this, 0048. But FFFE 4800 would also be a valid Unicode format. So it becomes a little bit complicated, but let's have a look at this thing. Another encoding was proposed in California, mainly for English language. Okay, why? They noticed one thing. Everything around them happened in the English language. Okay, nothing strange because, as I mentioned, this coding was proposed in California and English is quite popular there. So, what was proposed here? Characters from 0 to 127 are stored in a single byte. So, typical English text will use 1 byte per character, no problem, nice. Other code points will be stored in more bytes, but not necessarily in 2 bytes. In 2, 3, 4, 5, or 6 bytes. This means that for most English texts, UTF-8 is identical to ASCII, but for non-English text, it's less efficient, but still possible. Less efficient means that if you think about, for example, a sentence in French, Spanish, Swedish, even Icelandic, most letters there will be the letters we use in English, 26 letters of English alphabet. And only a few words will be special with special characters a little bit different than our letters A to Z. And what happens? Some range of the numbers of the code points, if they are from 0 to 7F, they are normally represented in a single byte. And because these are low numbers, we are guaranteed that this byte will start with a bit 0 at the leftmost position, the most significant position. Then we have a range of characters from the code point 80 to 7FF. And these characters will be broken down into 2 consecutive bytes. But these bytes will have some range of bits specifically set. So the first bit will have the most significant bit like 110, and the second byte will have 10. Okay, decoding this, each time you see 110 and 10 at the most significant part of the byte, this means that you have to extract 5 bits from the first byte and how many? 6 bits from the second part, put them together, and this is how you get this representation from code point 80 to code point 7FF. So as you can see here, the farther we go with those code points, the longer representation becomes, and also this identifier in the beginning of the first byte gets longer and longer. So any word that would, any character that would start with binary sequence 1111, sorry, 111110, okay, would be a 6-byte representation of something that is in incredibly rare code point 0460 to 7FFFFFFF. Okay, so this representation, UTF-8, can represent most characters on just a single byte. And please note, again, if you are writing a text in, let's say Polish, why not? Like 90% of letters, maybe 95% of letters are still typical letters like A, B, C, D, so they will be represented as a single byte. And from time to time, there will be Polish characters are actually here in this first part here. So Polish special characters will be represented by 2 bytes. So it's not so bad for non-English languages. But absolutely incredible is when you think that with this proposal, with this standard UTF-8, you can represent in total 4 billion different characters. And this can really cover most, if not all, languages of the globe. One very important thing about coding characters, it doesn't make sense to have a string or a text without knowing what encoding it uses. It concludes our topic of representing numbers in computing. Thank you for watching, and I invite you for the next part of these lectures, which will be about logic of computers. Thank you.